Welcome back to chapter 43. So we left off talking about MHCs and we talked about how they kind of determine what our cells are and what our cells are not. So we can kind of identify our own cells. But there's another important thing that MHCs can do, and that's to present antigens. So they can actually grab some of these proteins that are in whatever pathogens around. It could be a virus, a bacteria, and they can take and oftentimes stick those at the end of an MHC, and that way a passing immune cell can read it to see who's in the neighborhood, what bad guys are around. And so this process will be critical for our immune system to function and to have a specific immunity. Because to get a specific immune response, we have to know what antigen we're responding to. And so this will be taken care of. You'll see a common antigen presenting cell will be a macrophage, but there are others. But any cell that has these MHCs that will stick an antigen there can be used. So once again, we've said kind of every cell has these MH1s, but the MH2s will be more like specifically macrophages, T cells. They're going to be cells that are immune cells. So this allows T helper cells and cytotoxic T cells to go through and read the antigens that are around, and this is what really starts our immune system off. This is what lets us go attack stuff. Now, there are two types of immune responses that we can start off. So when we're trying to detect who's around, we can activate two separate things. The first one, humoral immunity, is going to be activating the B cells, which will cause antibodies to be produced. Now, this will go after very effectively smaller stuff, so bacteria, chemical toxins, viruses. The other pathway we have, which can be activated simultaneously, it doesn't have to be just one or the other. In many cases, you'll activate both. And that will be cell-mediated immunity. So this will be T cells. Specifically, this will be the T cells called cytotoxic T cells, or sometimes they're called T sub C. These are the ones that go around and actually kill cells by releasing a protein that will poke holes in the cell and make it die. So they'll go around attacking stuff, and these guys can go after smaller stuff, bacteria and viruses too, but they can also go after bigger stuff, including fungus. So if you have athlete's foot, yeast infection, things like that, they can go after protozoans, which would be things like malaria, giardia, and they can go after even larger parasites that we have. Anything that's pretty much not us, they can go after. But antibodies, because they're just these really small proteins, they don't do a really good job if you're talking about large eukaryotic cells. Because the T cells just kind of poke holes in things, any cell they poke a hole in leaks its insides out and dies. And so it's not really tied to something being small because of that. Now, helper T cells, these guys don't directly kill anybody. That's kind of their task. But what they will do is you'll have these helper T cells go around and they're going to look at these antigen presenting cells and look to see who's in the neighborhood to help activate these processes that do destroy stuff. And so they've got this protein called CD4 that helps them read these MHCs and the antigens that are there. And then if they can get activated, if they find an antigen, they can get activated for that antigen and secrete something called interleukin. There's technically two types, and you might see them called cytokines. There's lots of different terms. But in general, they secrete this guy called interleukins, and that will cause the activation of the cell-mediated pathway, as well as it can cause the activation of the humoral pathway. So these are kind of cool where it can either activate both of these separately, and if you have the cell-mediated pathway become active, they can actually use the T helper cells as a go-between to activate the humoral. So this one's kind of the messenger that makes sure that everybody's all set and ready to go for a specific antigen within our body. This is also the one that if you have the HIV virus, this is the one thing that it targets the CD4 protein. And so the cells that have those get destroyed, which then makes much of our immune system fall apart because this is the guy that typically activates everything. So if we can't properly activate things, we can't properly fight things off. And so that's why HIV can become AIDS, acquired immunodeficiency syndrome, where your immune system's just not working. It's also why some people are kind of immune to it, because they have a modified CD4 protein, so HIV can't target them. Now, the cell-mediated response is one that can be initiated without the T helper cells helping out. And so these are other T cells that are going to read class 1 MHCs. So you'll see the T helper cells, they'll tend to read the immune cells as well as the regular cells, whereas this is just going to look at our normal nucleated cells throughout our body, using a protein called CD8, so it's a slightly different protein, and they're going to read them to see who's in the neighborhood, and they will activate the appropriate cytotoxic T cells in response. And these are the killers that go around using this protein perforin, as we said, that will essentially, in a cell, form a ring of proteins that then allows the insides to spill out. So it perforates it, makes a hole in it. So these guys will go through poking holes in it. Now, afterwards, or I should say because of this, it allows us to go after a variety of cells that are within the structure, although this won't typically go after chemicals. This is going to go after actual cells, up from prokaryotic cells through our own cells that may have been infected by viruses or cancer that are presenting a specific antigen so we can target them. So it's not like all of them always present something that we can see to go after, but so long as we can see that antigen, it allows for cytotoxic T cells to target whatever cells have that antigen and destroy it. Now, the humoral response, our B cell response, is oftentimes referred to as the T-dependent response, because this one will not be activated by itself. This one is going to be activated either by the cytotoxic pathway being activated first, the cell-mediated, or it's going to be activated directly by a T helper cell. But usually a T helper cell is what activates it anyway. Either it does it because the T helper cell found it first, or the T helper cell found that the cell-mediated response already was there, so it kind of saw this cytotoxic T cell, used that and got activated, and then went over. So this one's going to rely upon us getting these T helper cells able to be activated first, and then they will go through and they will activate our B cells. And so our B cells, once they're activated by that interleukin we said, will turn into plasma cells. And so these are the workers that actually make antibodies, and then the memory cells that are going to sit around waiting so that they can, in the instance of a secondary infection, be ready to go so we don't have to worry about waiting as long the second time around. Okay, antibodies themselves are all going to have a fairly similar structure. I'm not going to go crazy with this. You might see them say long chain, short chain, whatever. The key thing here is that you're going to have on an antigen, there's going to be a little region called an epitope. And on the end of every antibody, there's this variable region that varies based upon which particular antibody this is, who it's attacking. And so this end region will be matched to whatever this epitope is for a specific antigen. So each antibody has a specific target then, and this is why it takes some time to make sure we're building the right antibody that has the right variable region to go after an epitope to take care of it. There's also going to be multiple types of antibodies. This is significant because some of them can do things like go across the placenta, and so it can help a mother essentially provide antibodies to help her child fight off stuff. Some can go across via breast milk, and then some of them will not. And so we're not going to get into the specific types that much, but just understand there are a variety of different types. Not all antibodies are created equal. Now, antibodies can do a variety of tasks to get their job done. The first is they can neutralize it, so they could essentially bind to the region of the virus that attaches to a cell. And so by doing this, the virus isn't like ripped apart, but the virus is now incapable of attaching to a cell and infecting it. So they've effectively neutered it or neutralized it without killing it. Some of them will just do what's called agglutination, where they clump up a bunch of the antigens with antibodies, and so now that it's all clumped up, it's A, harder for the antigens to do their job and attack us, and B, it's easier for white blood cells to come through and do cleanup. So typically these phagocytic white blood cells can come through and just munch up those clumps and take care of the problem. For some of our particular like toxins and such that are soluble, this can allow them to be precipitated, so now that they're solid, now that they're insoluble, it allows for us to have a cleanup crew, usually once again white blood cells, to come through and take care of it, break those down, and get rid of them. And the last thing they can do is activate the complement fixation pathway, which is a series of a bunch of different proteins that ultimately pokes holes in a cell and allows it to rupture. And so the complement fixation is the one pathway that directly just leads to the death of the cell in question. But it's not the antibody technically doing it. The antibody is just acting as a impetus, a signal, to start the rest of this cascade that occurs of proteins that ultimately leads to us destroying the cell. All right. So now we're at the end, or approaching the very end here, and so let's talk about how we can kind of trigger our immune system and the different ways that we can become resistant or immune to pathogens. So active immunity means you have an immune response. So something happened that you literally went through this full immune response of making antibodies, triggering your cell-mediated response, making cytotoxic T cells. And so this can happen two ways. The natural way, which is you got sick. Congrats, you got chickenpox. You now have an active natural immunity to chickenpox. Then there's the artificial way, which would be a vaccine, if I spelled that right. And so that would be, I gave you some really messed up viruses from chickenpox, but the antigens are still intact. So even though it couldn't put up a fight and really attack you, your immune system still was able to lock in on that antigen, produce the antibodies, produce the cytotoxic T cells, produce these memory cells, so I still have this immunity even though I never actually had to get sick. So that's going to be our active types. Now passive types means I'm going to get it from something else. I'm not actually making my own antibodies, which is what happens when you have an active response. So the first way is passive natural, and this is going to be things like nursing. And so breast milk contains antibodies. And so if I am a child, typically if you're less than 6 months, the child has a pretty poor immune system. And so the mother is going to be secreting antibodies, some of them at least, into the breast milk that the baby can then use to ward things off. So the baby didn't get sick. The goal is the baby doesn't get sick. But the baby doesn't get sick because it's being provided with the results, essentially, of getting sick, the antibodies, via breast milk. The other option is you can have certain things like injections. The one that comes to mind is like the rabies, not vaccine, but the rabies shot, where they go through and they get antibodies that were produced by something else. So they'll use like another animal to produce these antibodies against the rabies virus. And because our body typically cannot produce antibodies fast enough to fight off rabies, they just give us injections, and so you get a bunch of injections of those antibodies. So I'm artificially getting them. The goal is you never get sick. You don't want to get sick with rabies. That's not cool. You die. And so ultimately you're just going to bypass this and use antibodies from somebody else, but it's not natural. You're not like getting it through nursing. You're getting an injection, much like you did with the vaccine. And then with humans, there's other cases where we care about kind of our normal antigen responses. So one of them will be like blood typing to make sure if you're getting a transfusion, because remember the A is a specific antigen and so is B. O is the lack of one. And so if someone with O blood type who has neither of these antigens gets either of them, they will attack the blood. So this is why the person that's AB is considered the universal acceptor. Wow, that is horribly written. Acceptor. And a person that is O is considered the universal giver because they don't have any antigens on their blood. So if you give their blood to like me, as a person who has A blood type, I don't see any antigens, so there's no reason for me to have an immune response because there's no antigen to trigger the immune response. And the Rh factor is another blood antigen. There's actually more than these, but these are the common ones. Plus means you have the antigen, minus means you don't. So if you have negative blood, that means that you can only get blood from other negative people. If you have positive blood, you could get blood from either. This becomes an issue if the mother happens to be negative and the child happens to be positive, because the mother can actually send antibodies against this positive antigen through the placenta so she can start attacking the child while in the womb. So this can sometimes be an issue, and if you happen to be a female that has a negative blood type, you might want to be careful, especially if you're with someone where the father essentially has a positive blood type, because the negative is essentially recessive. But if the father is positive and the mother's negative, there's a decent chance that the baby will be positive, and you normally have to take some drugs just to prevent you from starting child abuse while the baby's still in the womb. All right. The last little bit that we're going to get to here is some more of these screw-ups. We brought them up briefly before. So allergies are where you detect a particular antigen that's just normal. It's pollen, it's peanut butter, it's a chemical that triggers an immune response, but it's non-lethal. But it can become lethal because your body in response to this starts this inflammatory type response where you get a whole bunch of dilation, so a bunch of blood goes to the site, goes to some area, if not the whole body, and then it starts to become permeable, so that way it allows for white blood cells and fluid to pour into those tissues. So we said it causes swelling. The problem with this, though, is when all that fluid essentially leaves your blood vessels to go into the interstitial fluid, you get a drop in blood pressure. And that drop in blood pressure can be fatal. They call it anaphylactic shock if you get a big enough response, and it can kill you. So peanuts can kill you, even though peanuts are not deadly by themselves. You know, they're not like a toxin. It's your body overreacting. It's a hypersensitive response. It's overly sensitive. And so that's why some people will carry things like this EpiPen, which causes vasoconstriction. So it essentially counteracts this to buy people time so they can get to the hospital and they can get this sorted out so they won't die from the allergy response. Then autoimmune diseases, same idea, where essentially you find some antigen on a type of our own cells and decide to go after them. So there's a whole bunch of these different diseases that can go after nerve tissue, that can go after your joints, that can go after the cells that produce insulin in your pancreas, that can go after, if you're talking like Crohn's, digestive cells. There's a bunch of these different diseases where we see it's a screw up where your body decides some of your own cells are essentially a problem. And so you have to cope with the results. And then we do have immunodeficiency diseases. There's SIDS, there's AIDS, there's a variety of these where for one reason or another you're either born where you're not producing enough stuff, that's like bubble boy SIDS, or you can have AIDS where you have a virus that's damaging your immune cells, and so now your immune cells can't properly do their job. And so because you have a compromised immune system, opportunistic diseases that normally can't fight us off can actually come in and do serious damage. So you can get fungal infections, you can get certain types of cancers that almost always our body clears up itself, but without any protection, there's not much you can do, and so that's why it becomes dangerous.